We have another interesting example for you with the local static variables, so with function templates. You'll remember I mentioned that the compiler is going to generate a function definition based on your type argument. That is one definition per type. Now you can think what's going to happen when we use static variables with our template functions. In this example I have a global variable which I just named g, and I set that to 0 by default. Then I have a template function called increment. It has a default argument which I set to int, so a default type argument. Then I have a local static variable L which I set to 0, and I'm going to print out cout global variable and a pre-increment g. Okay, so we start at 0 and this will print out 1 to begin with. Then we print out local static variable and we also pre-increment L, so this static local variable here. In this example we are not actually going to use the type parameter in the definition. We'll just provide a couple of type arguments for that function so that the compiler will generate different versions of that function. Here, the first two invocations, it's going to use the default type argument. Alright, and then we explicitly specify the type argument, so double, and then char. Now you can think for a second what's going to happen when I build and run this program here. Alright, I'll build and run, and we'll see what we get. For the global variable we get what we may expect, so we get 1, 2, 6. It gets more interesting with the local static variable. We get 1, 2, 1, 2, 1, 2. And that's because again the compiler is going to generate different versions of the function based on the type argument. And how many different versions is it going to generate in this example? Well, it's going to generate 1 based on the int. Okay, the default argument is int. 1 for double and 1 for char. I'll just make sure the syntax is the same, so I'll remove all of those explicit type arguments and we'll use int now, the default type argument for all of those function invocations. Build and run. And now we will get 1 to 6 printed out for both the global variable and for the local variable. Because for that function, the increment function, the compiler is only going to generate one version of that based on the type argument int. And another quick example, I still have the global variable g, and in this case I have an entity struct template. I do inline static int L, and I set that to 0. Now to do this inline static, you have to go to project, the project properties, and this has to be C++17, the C++17 standard or later. It's just a bit easier to initialize it in this way. I still have this void increment function, but in this case it's a member function. Within the body of increment I print out global variable and I pre-increment that global variable, and then I also print out the local static variable, which I called L for this example, so I pre-increment L and I print that out. And in main I construct entity1, which is of type entity, and as a type argument I provide short, and I do entity1.increment twice. Then I construct entity2 of type entity, but in this case I pass in a type argument of char. Then I do entity2.increment 4 times. You can think for a second what the output is going to be of this program. Pull and run this, and let's see what we get. Once more to the left, the global variable is going to start at 1. Remember again that we use pre-increment, so it's going to print out global variable 1 to all the way to 6. And then for entity1 it's going to print out the local static variable 1 and 2. And then for entity2 it will start at 1 again, so 1, 2, 3 and 4. Remember, for entity1 we do increment twice, for entity2 we do it 4 times. That static variable here, L, will be associated with a particular type of that entity struct. The compiler is going to generate a particular entity struct definition based on the arguments, the type arguments that we pass in. In this case we have 2 different types, so we have short and char, so it will create 2 definitions of the entity struct. Again, in this example we don't actually use that type parameter in the definition of the struct. Just to emphasize this again, I'll change the second entity here, the second instance of entity, I'll go and change this to short as well, so where entity1 is of type entity, and we provide a type argument of short, and then entity2 is also of type entity, and we also provide a type argument of short. So the compiler is only going to generate one definition of the entity struct from that struct template. So if I build and run this now, you can think what the output is going to be. You can see the global variable prints out from 1 to 6, and the local static variable is also going to print out from 1 to 6. even though those printouts are from two different entities. Okay, we have entity 1 and entity 2, but the static integer, that is static variable, is associated with a particular class definition or struct definition. In this case, we only have one because both of those are specified as entity structs and we pass in type arguments of short. And the same is going to happen if both of these are integers, or even something like char, for example. Build and run, and you'll get the same result. Okay, so I hope you found this interesting. This again was just to demonstrate or to emphasize that you get different actual definitions generated by the compiler